Okay, in this video we'll talk about something called the integral test for convergence. And the rule itself reads like this. We'll just sort of read through it, and then we'll talk about what each part means. So first of all, it says that if you have a function f of x that's positive, decreasing, and continuous for any x that's greater than or equal to 1, and you can find a function that models a sequence, then the sequence and the function either both converge together or both diverge. Now, specifically, what does it mean? It's a little bit hard to picture what's going on here, so let's go through it a part at a time. So to begin with, here's what you're going to be given. You are going to be given this part right here. So you'll be given a sequence, and you'll be asked, does it converge or diverge? Now, graphically, let's just take a kind of quick look at this as we go through it. If I had one, if I were to graph this thing, it would look something like this. We'll put this, and this is going to be a sequence A sub n. And let's suppose it does this. So here's the points that make up a sequence A sub n, and there's a sequence. So now back to the rule. Now what the rule says is this. So starting with this is what you're given. Then the next part is this, is to find out whether this sequence converges or diverges, you're going to come up with a function that models the sequence. And that's what this part means right here. So at each value of n, if the value of the function is equal to one of the terms of the sequence, then you'll have a function that will go through each one of those points. And graphically, let's see what that would look like. So if the red dots represent the sequence, then this blue line is going to represent the function. So what this is going to be some function f of x, a continuous function f of x, that goes through those red dots. So as long as the blue line agrees with the red dots, that's what this statement right here says. So now you've got a function that models the sequence. Now the next thing you're concerned about is this, if you notice, whenever you're working with a sequence, it's only defined when n is in integer values starting at 1, 2, 3, and so on. So in this case, you're only concerned with the x's that are greater than or equal to 1. And this is going to be important, so let's take a look at that graphically. What that means is, if you were to come in here and say, here is 1, so I've got 1 right here. So I'll draw a line from here to here just to emphasize that I'm only concerned with the x's that are greater than or equal to 1. So only concerned with what happens to the right. Anything that happens over here, I'm not concerned with. And that's what this part is right here. Okay, now the next part says this. You want to know, does the sequence converge? Well, once you've got the function that models it, if you were to integrate that function from 1 to infinity, which is an improper integral, if that integral settles on a fixed number, then you'll know that this integral converges. Now, graphically, what that's going to look like is this, is you're going to find this area from here, and we'll just kind of shade it as it goes in all the way over to here. So if you evaluate the integral, you'll get that green shaded area. And again, if it turns out to be a fixed number, then the integral converges. And what this rule says is this, is if the integral converges, then the series also converges. But if the integral diverges, then the series diverges. So whatever happens to the function, the same thing is going to happen to the series, and you'll know whether it converges or diverges. Now there's one more thing that you have to pay attention to, and that's these three conditions up here. This rule only works if the function that you're using to model the series is positive, decreasing, and continuous. And again, let's graphically take a look at each one of those just to see what they look like. So first of all, let's look if the function is positive. Now what that means is that the blue line then, if it's positive, it has to be above the x-axis. So in this case, the blue line is entirely above the x-axis, the function's positive. Second condition says that it has to be decreasing. So as you go way off to the right, the function has to be going down continuously. In this case, clearly it's decreasing as you go off to infinity, so it satisfies the decreasing. And then finally, it has to be continuous in the interval. So as you go way off here to the right, it can't have any asymptotes in it, can't be undefined. In this case, it is continuous. So this blue line satisfies all three of these conditions. So now with that little bit of an overview in mind, let's take a look and finally see what an actual problem would look like. And the problem starts with this, and most people will do this, just to be honest. Most people put the integral test off to the very last test, because this thing usually turns out to be pretty long, pretty involved, and before you get finished, you're going to be working with derivatives, you'll be working with improper integrals, you might be working with U substitution, integration by parts. Any of the integration techniques that you've had before might pop up in this. So again, most people will try all other tests for convergence that are easier before they get around to this. And in some cases, I may be working a problem here that you could solve easier with another one, but we'll just do this one as with the integral test just to show you how it works. So again, here's what we want to find. Here's a series, 3 over 4n plus 1, and we want to know, does it converge or diverge? Well, going to the rules, the first thing you're going to do, you're given this right here, and your very first step is to come up here and to find a function that models this series. So let's do that. What that's going to look like would be this. I'll make it be rather than having a summation, I'm going to change it into the integral from 1 to infinity of, and I'll put it across here, we'll make this be 3. And the only difference is rather than 4n plus 1, we'll change it into a function, a continuous function in terms of x plus 1 dx. So I want to evaluate this. If this integral converges, then the series converges. If this integral diverges, then the series diverges. But on these problems, and this is what makes them take so long, is you can't use any of this unless you first of all show that this function satisfies these 3 conditions. It has to be positive, decreasing, and continuous. So let's do that first and see what it looks like. First of all, we'll look at, is the thing positive? So I think I'll come down here and we'll check this. We'll check to see, is it positive? And I'll put a little question mark there. So is this function positive? Now again, to test that, this is going to be the first thing that we're testing. I'll do it this way. I'll have 3, then divided by 4. Now remember, x's have to be greater than or equal to 1. So any x that I put in there, I'll just put a positive to represent that it's a positive number. Now in that case, you're going to have 3 in the numerator. You're going to have a positive in the numerator. And since everything in the denominator will always be positive, you'll have a positive divided by a positive, which is positive. So yes, it passed the first test. So now you move on to the second test. And the second test says that, is it decreasing? Now, before we go on to decreasing, let's take a quick look at our graphs one more time. We'll go back to this again, and I'll use black, I think, on this one. If I have a function and I want to show that it's decreasing, you might remember that you can use the derivative to help you decide that. So the idea is if I pick any point in the interval that I'm interested in, I'll go back here and pick this. So I'll pick this point right here. If I were to draw a tangent line there, then the slope of that tangent line is the derivative. So remember, if it's negative, then the function would be decreasing. If it's positive, then the function is increasing. So the question is f prime negative? If you can show that the derivative is negative, then that tells you that the function would be decreasing. And that's just from previous work that you've done on there. So again, to show that a function is decreasing, find its derivative. If the derivative is negative in the interval that you're interested in, then the function has to be decreasing in that interval. So that's what we'll do. So let's turn this thing back off and go back here. And in the second step now, it's going to be this. I want to know, is this thing decreasing? So is it decreasing? And I'll put a question mark. Now really that's the same thing as saying, is the first derivative negative? So if it's decreasing, the first derivative would be negative at every point. So what this means is the first thing you got to do is find the derivative. So the derivative of this thing, and here you have to use the quotient rule. So it's going to be the denominator times the derivative of the numerator, which would be 0, minus the numerator times the derivative of the denominator, which would be 4, all divided by the denominator for x plus 1 squared. Now what this is going to be, this is going to be, this entire thing, right, 0 times anything, this thing right here will all go to 0. Minus 3 times 4, you'll have a negative 12 in the numerator. And then in the denominator, you'd have 4x plus 1 squared. Now the question is this thing positive or negative? Well, remember, you can only pick x's that are greater than 1. Whatever x you pick, when you square it, the denominator will always be positive. You've got a negative 12 in the numerator, so the numerator will always be negative. So you've got a negative divided by a positive, which is going to give you a negative. So you know that f prime is decreasing. And is this thing decreasing? Yes. So is it decreasing? It was yes, it is positive, and yes, it is decreasing. And it's decreasing because you showed that the first derivative is negative. So now you've got a third part. Again, a lot of work in these things. So let's go back up. You've showed that it's positive. You've showed that it's decreasing. Now the question is it continuous? So we'll move on to number 3 down here. And the third question you have to answer is it continuous? And all this is before you even get started with the integral. So is it continuous? Now again, I've got, if it's continuous, on a rational function, the only way it could not be continuous is where the denominator is equal to 0. So in this case, I'm going to set the denominator, so the denominator equal to 0. So that's going to give me 4x plus 1 is equal to 0. If I solve for x, I would get x is equal to a negative 1/4. Now what this is a place where the function is undefined. And what this would look like, let's go ahead and go back to our graph, and you can kind of see it on the graph. So when x is equal to a negative 1/4, the denominator is equal to 0, the function is going to have an asymptote. So graphically what that looks like, and we'll go back to this thing again, is over here, and let's suppose that negative 1/4 is about right here. That means I've got an asymptote that goes in something, and it would look kind of like this right here. So an asymptote that goes through here. Now, remember, you're not concerned with anything that happens to the left over here. As a matter of fact, if you were to actually graph that, let's just go ahead and continue this up. If you did the actual graph of the function that we're working with, it will go up like this, hits an asymptote, goes over this way, and then it also kind of comes in like this, and it does something like that. So it does that. So the function is undefined, but again, you're not concerned with anything that happens less than 1. You're only concerned with what happens from here going off in this direction. So in the interval that we're interested in, the function is continuous. So we'll go back to our problem now. And in this case, it's undefined here, but this negative 1 is outside the range. Remember, you're only interested in the positive. So it is continuous everywhere in the interval that we're interested in. So we'll put here, we'll put yes, it's continuous. Yes. So it actually satisfied all 3 things. It is positive, it is decreasing, and it is continuous. So now with all that out of the way, finally you can begin to solve the problem. Again, you begin to understand why everybody puts the integral test off to the last test. So let's go back up now and see what we're trying to do. So now that we've satisfied these 3 conditions, now you can do this. And at this point, it becomes just a question on improper integrals. I always tell, using my students this, is if it's been a while since you've done improper integrals, I would stop at this point, go back and watch the video on improper integrals so that you can remember how to do all this. But we'll run through a sample problem right here. So what happens is this goes off from 1 to infinity. Now, if you want to find that limit, again, in an improper integral, what you do is rather than going from 1 to infinity, you're going to go from 1 out to some point, we'll call it b, of 3 over 4x plus 1 dx. Then you'll take the limit as b approaches infinity of this thing right. We're going to put this in bracket. So again, rather than find the integral from 1 to infinity, find the integral from 1 to b, then take the limit as b goes to infinity. And that's improper integrals. If you need to, review that technique. Now, the next thing is that even in finding these improper integrals, you still may have to do things like use substitution. So let's go up here, and just a reminder, you have to recognize the form. If this thing started out as the integral of 1 over u du, and a reminder that's equal to the natural log of u plus c. See, the idea is to recognize that with use substitution, this thing's actually a 1 over u problem. So I'm going to go ahead and rewrite that, and I'll rewrite it something like this. I'll make it be the limit as b goes to infinity, and I'm going to do this to it. I'll make it be the integral from 1 to b, and I like to write them like this on use substitution. This is 4x plus 1, and I'll move this over to the side and make it be 3 dx. So I want to do use substitution to solve this. And a reminder what the use substitution would be like. If I let u be equal to 4x plus 1, and then take du dx, and this is just plain old use substitution, that's going to be equal to 4. Therefore, du would be equal to 4 dx. Now again, I've got a 3 dx, so I'll take the 4 and bring it over. That tells me 1/4 du is equal to dx. And then finally, I've got the dx, but I need a 3 dx, so I'll multiply both sides here by 3. This one times 3, and this side times 3. And what that's going to finally give me then would be 3/4 du would be equal to 3 dx. So this is the use substitution right here. Now this part right here agrees with this part right here, so I can swap that out, and I'll trade it out for 3/4 du. So let's go ahead and do that. That's going to give me the limit as b approaches infinity, and this would be the integral from, and I'll leave them for a while at least in terms of the x limits. This would be 1 over u, and in place of 3 dx, put 3/4 du. So that's going to be 3/4 du. Okay, so what this is going to give you, this would be the limit as b approaches infinity. And I'm going to do this. I'll go ahead and bring this 3/4 outside. So that's going to be 3/4 the integral 1 over u du going from 1 up to b. Now what this would be, and again, I'll still have the limit as b approaches infinity of, here's the 3/4. Now, the integral of 1 over u du, that's this thing up here. So the integral of 1 over u, it turns into the natural log of u. So this will be the natural log of u evaluated from 1 to b. Now, I never did change the x limits, so I'll make this be the limit as b approaches infinity of 3/4. And I'll change that u back into what it's equal to. So u is equal to 4x plus 1. So we'll put the 4x plus 1 back in right here. And now it's all back in terms of x again. Evaluated from, this would be 1 to b. So now it's just a matter of evaluating that. So I've got the limit as b approaches infinity of, and just take this thing evaluated at b minus this thing evaluated at 1. So I would have 3/4 of the natural log of 4, and in place of x, put a b plus 1, minus, now plug in a 1. This would be the natural log of 4 times 1 plus 1. So it looks like that. Okay, now at this point you're going to actually take the limit. So what this would be as b goes to infinity, then 4b will go to infinity. 4b plus 1 goes to infinity. The natural log of a very large number, this entire term right here, would go off to infinity. Now this term right here, that just turns into the natural log of 5. So what you've got is, as you let b go to infinity, this term goes to infinity, this is a constant, this will wind up not making any difference at all. That'll be the dominant term. The entire thing will go off to infinity. Now that means that this thing right here does not exist. It doesn't settle on a fixed number, goes off to infinity. And what that tells you, again, going back to your thing, this tells you that the integral, so the integral diverges. So it didn't settle on a fixed number. The integral diverges, which is what this is. So you showed that the integral diverges, but the point of the whole problem was to see what happens to the sequence. Well, what the rule says is if the integral converges, then the series converges. But in this case, the integral diverge, therefore the series diverges. So the last step in the problem would be, since the integral diverges, this tells you that this series also diverges. So a lot of work in these, and just kind of run through it one more time. Again, given an original sequence, find a function that models it. Again, you can't use the process unless it satisfies these 3 points. So the function has to be positive, decreasing, and continuous. So you need to first of all show that it satisfies all 3 of those. If it satisfies all 3 of those, then you can proceed to the integral. But doing the integral might involve, in this case, this one involved use substitution, it involved natural logs, it involved improper integrals. So there's a lot of work involved in just finding the integral. Now in this case, it turned out to be infinity, which means that the integral diverges. If it had turned out to be a fixed number, suppose it turned out to be 4/3, then in that case, that would tell you that the integral converges and the series would converge. So if an improper integral settles on a fixed number, it converges. If it goes off to infinity, then it diverges. And what the rule says is whatever happens to the integral, the same thing happens to the series, and there's your answer. Now we'll try one more of these a little bit later on, but at the end of this, most students are saying, I can understand why most people put this off to the very last test. These things just take a lot of work, unfortunately.